like we have scaled the velocity and the acceleration equations up to, by mass, to get to the momentum and force of the object on the spring moving back and forth between the three locations. Just as we've scaled those, we can do the same thing with the energy. Now, the first thing governing every system is that the total energy, in this case, this particular case of the object, the mass on the scale, is going to consist of the kinetic energy and the potential energy of the spring. But we know because of the law of conservation of energy that the total energy of the system remains constant. So the total energy remains constant, the initial, and it's always going to be the sum of those two things. So we then can mark our total energy like so. That's our total energy. We can look at our kinetic energy, which is going to be related to the velocity. And that kinetic energy equals 1/2 mv squared. But v, we said, is equal to minus v naught sine omega t. Because at 0, the velocity is 0. At the beginning, the velocity is 0. It accelerates, and it's a maximum, and then it goes to 0, and it comes back to a maximum and back to 0. So doing the algebra, then, we have 1/2 m v0 squared sine squared omega t is the kinetic energy. We'll set it times 0. At times 0, the kinetic energy is 0. And when we could complete this cycle, we see that it's a maximum at pi over 2 radians. Kinetic energy is a maximum at pi over 2 radians. And it returns to 0 at pi radians. And then at 3 pi over 2 radians, it returns to a maximum. And at 2 pi, it is 0. Now you notice, of course, with this being the 0 value, there are no values down here. Energy is a scalar. So it would make sense that it would behave like this. Not too pretty. And then when we get to the potential energy of the spring, well, that is 1/2 kx squared. And we said that x is minus x naught cosine omega t. So when we substitute that in, we get 1/2 k times xo squared cosine squared omega t. And in the beginning, our potential energy is a maximum. And by the time it gets to the middle, pi over 2, there is no elastic potential energy, so it's a minimum, 0. And when we get 2 pi radians, it is a maximum. And when we get to 3 pi 2 over 2 radians, it is a minimum. We're back to a maximum again. And what we can then see is that at any moment in time, if we take the sum of the red and the green, it will equal the blue. The kinetic plus the potential equals the total. And that total remains constant over time. Now, there are some interesting thing here then, that the total energy of this system can be then described as, the total energy of the system can be described as when there's a maximum, the maximum velocity. is at V0. That's the maximum amplitude. And the maximum, what I'm trying to say is that the total energy is at different times equal to the potential energy and out of phase equal to the kinetic energy. And so that's a way we can find out the total energy of a system. So if we wanted to know for example, the maximum velocity, well, all we need to know is the spring constant and the displacement of the maximum displacement. And from that, we know that this potential energy will be equal to this kinetic energy. We can find the velocity.